In this lecture, we're looking at a quantity known as angular momentum. Linear momentum was defined as p with a momentum vector is equal to the mass times the velocity. Angular momentum will be defined in a similar fashion for things rotating, for rotating systems, where capital L is our symbol for angular momentum. That vector is equal to the moment of inertia times the angular velocity. You notice that for linear momentum, p was in the same direction as the velocity. Similarly, for angular momentum, L is in the same direction as the angular velocity omega. Let's look at the angular momentum of a particle on a circular path. So here we see a particle, and it's moving around the z-axis in a clockwise fashion. And since it's going in a clockwise fashion, that means that omega, if you curl your fingers in the direction, your right hand fingers in the direction of the motion of the particle, then your thumb points down. So the direction of omega is down. So that L will also be pointing down in the same direction as omega. To figure out what the magnitude of L is, we're going to define two new vectors, a radial vector that goes from the axis to the particle, and the momentum vector of the linear momentum vector of the particle, as shown. So the magnitude of L will be equal to the moment of inertia of the particle times the angular velocity of the particle. The moment of inertia of a particle is equal to its mass times the magnitude of the radius vector squared. And the angular velocity in terms of the linear or tangential velocity is v tan divided by the magnitude of the radial vector. If we rewrite this a bit, canceling out one of the r's, we have the magnitude of r is equal to the mass times the velocity v tan. But the mass times the tangential velocity is the momentum. So that in general, for a particle, we can write that the angular momentum L is equal to the cross product of r and p. So that we can look at a general particle moving past some point A and ask what is the angular momentum of the particle as it goes past A. To do that, all we have to do is take the cross product of r and p. For many particles, the angular momentum of a system of particles is equal to the sum of the individual particles' angular momentum. So the sum on I of L sub I. Now Newton's second law in terms of momentum is given in this fashion, that F is equal to the time rate of change of the momentum. This is the linear momentum p. Similarly, the rotational form of Newton's second law can be written in terms of the angular momentum. So tau is equal to the time rate of change of the angular momentum L. So angular momentum is conserved, just like linear momentum is conserved, since there will be no change in the angular momentum if there is no external torque. So if no torque acts on the system, L does not change. So LF, the final angular momentum, will be equal to the initial angular momentum if no external torques act on a system. Let's take a look at an example. We have two identical disks, so they have the same moment of inertia. The bottom disk is spinning, but the top disk will be still. So initially the disks are separate, and the bottom disk is spinning, so it has an angular velocity omega sub bottom, pointing downward, for example. The bottom is spinning, so it has a value of omega sub bottom, but the top is not spinning, so omega top is equal to 0. The initial angular momentum, L sub I, is equal to the moment of inertia times omega sub bottom, plus the moment of inertia times omega sub top. But omega sub top is 0, so the initial angular momentum is just the moment of inertia times omega sub bottom. Next, the top disk drops onto the bottom disk and sticks, so the two rotate as one. So the final angular momentum is equal to 2 times the moment of inertia, since there are now two disks, times some other angular velocity, omega subtotal. And we want to figure out what this new angular velocity is. Well, LF is equal to L sub I. So we can write down that 2I omega subtotal is equal to I times omega sub bottom from up above, the initial value. Solving for omega subtotal, we have that omega subtotal is equal to half of omega sub bottom. And it's in the same direction as the original omega sub bottom and half the length. So that's the solution.